Hello, welcome back to the second part for this week. Today we'll start with assessing the fit of the simple linear regression model. So what we're going to look at is the sum of squares, the coefficient of determination, and then show you how to get this information inside of Excel. So the first thing you want to look at is your SSE, or the sum of squares due to error. Again, that's just subtracting the predicted value of y from your actual y, squaring it, summing that for each one of your observations. And we saw from the previous video, and if you're looking in your book, that SSE was 8.0288. So what we're looking at is trying to see what's the fit of this linear regression model. One thing you'll have to do is calculate what is your average dependent variable, and in this example it's our time, or y bar. So all we do is add up all of our y observations and divide by n. In our case, comes to 67 divided by 10, or 6.7. So that's our y bar here. And if we didn't know any other information, that's what we would use to predict what y is going to be for our travel time, or travel miles. From this graph, we can see that if that's what we were using, what would we get for observation y? So y is this amount, y sub 5 is this amount minus y bar, which is 6.7. We can see that it over predicts by a whole bunch. And then if we see y sub 3, then we could see that, it under predicts by a whole bunch. So restating what we just saw, then if we look at the table 7.3, it shows you how you get the sum of square deviations. Right? We're using our average y to predict the travel time in hours for each driving assignment and sample. So if we want to know what that difference is, the ith driving assignment, we just take that particular observation minus our y mean. So that's the measure of the error involved using y mean to predict that travel time. The next thing that we want to calculate is something called the total sum of squares, which is SST. Notice that this is a measure of how well the observations cluster around the y bar line. So that's just a straight line. So we're just doing y sub I minus y bar, which is in our case 6.7. Notice this isn't the predicted y. This isn't the y that got us the slope, the mx plus b equation. This is just the average y. And then when we subtract that from what we observed and square it and then sum all of that, that becomes SST. And that's just a measure of how well the observations cluster around that y average line, which is just a straight line across. So if we look at this table 7.3, they just show you how to do those calculations. Right, so y sub I, this one minus 6.7 gives you 2.6. Since this is less than 6.7, we got a negative 1.9. We just do all that. Right, and then we square each one of these observations, and we get an SST of 23.9. So notice here we've put in the equation for the regression line that the data clusters around the line more than it clusters around just the average for y line, which is right here. So the next thing we want to calculate is something called sum of squares due to regression. This is just the sum for each of our observations, which would be our expected y hat, that's from the equation, the linear equation, minus y bar, which is our average y, which if we didn't have a line, this is what we would use. So this measures how much y hat values on the estimated regression line deviate from y bar. So to bring all these together, the sum of total squares is equal to the sum of squares due to regression and the sum of squares that is the residual, or due to error. So you've got all these values here. So if you know two of these values, you can calculate the other value. I'll repeat that. If you know two of these values, you can calculate the other value. Now you may be asking yourself, why are we going through all these calculations? Well, we're going through all these things because we can get something called the coefficient of determination. And that's a ratio of SSR over SST. And that'll give you the goodness of fit for your estimated regression equation. And it's denoted by R squared. Right? It takes on a value of 0 to 1, 1 meaning perfect correlation, 0 meaning no correlation, or no coefficient of determination is not related. That's what it would be telling you, is that your x value is not related to your y value at all if you have a coefficient of determination of 0. Now if we go back from when I did this in Excel and we look at that regression analysis, we can see that it's giving you those numbers that we're going to be calculating. Also note that when I did this chart, I clicked off this value here, and so we've got that coefficient of determination listed right on our screen here. We didn't have to hand calculate it. And remember, we got to that by when I clicked on this little plus sign here. I went to trend lines, expanded that out. I went to more options, and when I scroll down here, I can click that right here to display our value on the chart. Just go back here, close this down, and so I've got that listed there again. But that's how you would get that through Excel. So let's look at this output from our regression analysis. We can see the total here is equal to the sum of these two. So if I widen that up a little bit, we got regression and residual is equal to the sum of the total. So to get our R squared, it's nothing more than the SSR divided by the SST, and it's 0.66407 or 6641. I would leave it at 4, 1, or 4 decimal places. And what that is saying then is that 66.4% of the total sum of squares can be explained by using the estimated regression equation. That is, y hat is equal to 1.2739 plus 0.0678 times x1, or this line here. That's where I'm getting those numbers from. So that also means that 1 minus that value of r squared is what can't be explained. So to me, I mean, this is good, and it depends on what kind of work you're doing. Some work, say in sociology, if it's over 0.4, that might be considered significant. Others might say it needs to be at least 0.8. It just depends on your area that you're working in and the numbers that you have on whether you want to say this is good or not. So if you're following along doing this in Excel and following along in the book, you should have a chart that looks like this that has the y. This is y hat right here. Linear regression model equation, and then your r squared model. Or I should say the r squared value, which is the coefficient of determination. All right, the next thing we want to talk about then is the multiple regression model. What happens if you have more than one variable that's independent trying to predict y? And it follows the same outline as doing a simple linear regression model. And we'll look at the least squared method and multiple regression here. So the multiple regression model looks like the following. So y predicted is equal to beta 0 plus some beta 1 times x1, the first variable, beta 2 times x2, the second variable, all the way out to beta q times the q variable, plus some kind of error term, and that error term accounts for the variability in y that can't be explained by the linear effect of the independent variables. So it's just like the simple regression model, except we're just adding more independent variables. Also note this is for the population. So again, we'll go through that process of calculating a B, which is an estimate for each one of these B's. And so when we look at each one of those B's, they represent a change in the mean value of the y, which we're trying to predict, that corresponds to a 1 unit increase in the independent variable x. So whatever b goes with j, x sub j, it's just whatever independent variable we're talking about. So now the expected value of y given all of these x's is equal to this equation now. And the estimated value of y hat, is equal to b0. We just replace the betas with the b's. These are point estimates for the betas. And that y hat is the estimated mean value for y given all those independent variables. We go through the same sort of rationale for the least squares method, but now it's multiple regression, so we're trying to minimize the difference from what we observe minus what we predicted with y hat, and that's just the minimization of those residuals or those error terms. So if we look at the last equation on this slide, we've got y minus y hat. We substitute what we still use what we observe, y sub I, minus whatever the value that's shown for when we put in that estimated equation for that particular y. And that's just, when we square that, that's just that error term. So going through that same process again, then we've got here is our multiple regression model. We have some data that we're collecting. We estimate the B's, and the B's provide estimates of the betas for each one of those independent variables. And hopefully they are good estimates. Recall from our initial simple linear regression, that is, we only have one x to predict one y, our r squared value was 66.41. If we subtract that from 1, then that implies that 33.59% of the variability remains unexplained. So that's a lot of variability that's not explained by that one variable. So as someone who's making decisions, you might want to think about it. Are there any other variables or information that would help me predict y? So in our case, you would think about adding more variables to your equation. That's where we get to the multiple regression. And so then we have our y hat. What we're predicting is equal to this equation now. We're just adding an additional b sub whatever number it goes with the independent variable that we are using. So now we're adding number of deliveries. So we're only adding 2 independent variables now. So distance traveled and the number of deliveries might help us predict the time, or mean travel time. We still calculate SST, SSR, SSE, and R squared as the computed values that we did earlier. And we can get all that information by using Excel's regression tool. And we get to that by going to our data tab, going to, I'll scoot that over so you can see it, our data analysis. We'll select regression, and then we can select what we'd like to look at. And I did the confidence level of 99% because that's what your book had earlier. And it'll generate a page similar to this one. And here are your residuals. And what we're showing in, let me minimize this, in the slides here are going to be for the 2 variables. So notice here your input range is going to be your D column and for your Y range, and then the input X is going to be your B column to C. So B and C contain your independent variables. So just make sure you set it up for that. And that will generate something like the following. Notice that this is a lot different, not a lot different, but different than what I just showed you for one variable. So here are your intercept values. So that's your B0. This is your B1 for miles right here. And this is for deliveries. This is your B2. And so for that, you would write your equation. Note here that your R squared, this one, the second one here, is 0.8173. So what that's saying is that 81.73% of the variability in the sample is now explained. And so adding that extra variable means we can now explain more of the variability in y, or a dependent variable. So if we visualize the results of what we've gotten, then it's no longer a line which we are diagramming, but a plane, because now we have an x-axis, a y-axis, and a z-axis, or when we put variables on those, we've got x was the delivery time. Let me get this straight here so I don't confuse you. X was miles, and we wanted to say how much time you spent. So that was our y. So typically we would have looked at it from this perspective and then going up or down. But now we've added the number of deliveries here, so that's another dimension, if you will, and that's how they get to this plane. The next thing I want to talk about is some inference and regression. So what are some conditions necessary for valid inference when you use the least squares regression model? How do you do some testing on those regression parameters? Are those good betas or not? It could be that those betas might fall in a confidence interval that would include 0. So then they wouldn't be very good for using as an estimate. And then we'll also look at looking at non-significant independent variables, should you use them or not, and then the concept of multicollinearity. So with that, we have a concept called statistical inference, and that is the process of making estimates and drawing conclusions about a characteristic of your population. Remember, all those betas, the B's I should say, were estimates for the betas, and the betas were the actual values for the population. So typically we want to draw conclusions about those. But before we can, we need to think about some hypothesis testing of those betas and come up with some interval estimations. So in order to make any inferences about the model you just created, that is to predict y, you have to meet the following conditions. And those are that for any combination of the values for your x's or independent variables, the population of your error terms is normally distributed with a mean of 0 and a constant variance. That's the first rule or condition. The second one is that your error terms are statistically independent. So here we have a graph of the expected value of y given x, and seeing how those conditions are being met. So we have y going this way and x going this way, and we have different values of x, and we can see that what y predicted is at each one of these x values. What we're showing here is the distribution of the error term, and so we can see that they're normally distributed with each same variance. We can also plot the residuals and predicted values of the dependent variable. Right? So this chart of residuals and independent variables are a way of assessing whether the conditions are violated. So what they're saying is you should review the scatter chart for patterns in the residuals, and then from there you can see if one or more of those conditions have been violated. What you're really looking for then is the residuals are scattered around 0 throughout your predicted values of your independent variables. So this looks fairly random. So here are some examples of scatter charts for residuals on different regressions, and you can see they're not that random. There seems to be some pattern there. A lot of these are below, and then you got a lot that are above, that they're not closely around the 0 value. And here, this is all over the place. So if we look at panel A here, that variation in residuals increases as the value of the independent variable x increases. So what that means is then the residuals probably do not have a constant variance. In panel B, the residuals are positive for small and large values of your independent variable, but are negative for moderate values. When we plot the residuals for the Butler Trucking Company, this is what we see. So the miles residual plot and the deliveries residual plot. So for the miles one, it looks like they appear to have a mean of 0 and similar variances around the 0 area. And the same thing can be said for the deliveries. That is, they appear to have a mean of 0 and to have similar variances. And we can generate all of those values by just checking that residuals box when we do Excel regression analysis. And so for that second Butler spreadsheet, this is what you would get. And if we graph those scatter chart for predictive values of Y and residual E, this is what we get. So the next thing we will look at is this testing individual regression parameters. That is, we want to know if there is a statistically significant relationship that exists between our dependent variable Y and our independent variable X. Okay, so is X significant to adding to explaining the variance in Y? So one thing to think about is if the beta is equal to 0, then there's no linear relationship between Y and that particular independent variable X. If the beta for that particular independent variable is not 0, then there's a linear relationship between Y and that particular value of X. You may want to listen to this slide several times. So a test that we can run is a t-test to hypothesize that the regression parameter is 0. And that test statistic is t is equal to the beta divided by the estimated standard deviation for beta. So as t gets bigger, we are more likely to reject the hypothesis that the regression parameter beta is 0. So we want a big T here. So smaller values here gives us a bigger T here. If you think about that. And we're in luck in terms of having statistical software that will generate p-values for us. And we know if the p-value is less than the alpha value, we reject the null hypothesis. What that's saying is that for a given value of t, the p-value represents the probability of collecting a sample of the same size for the same population that yields a large t statistic given the value of b, or beta I should say, is actually 0. So as I mentioned earlier, we're going to test to see if these beta estimates are statistically significant. That is, they don't contain 0 in their interval range. So some terminology that you've already seen is this confidence interval. So that's an estimate of that population parameter. Remember, these are betas, not b's, that provide an interval that contains the value of the parameter at some level of confidence. The confidence level indicates how frequently that interval estimate based on samples of the same size taken from the same population using the same sampling technique will have the true value of the parameter we're estimating in it. What you don't want to see is that in this confidence interval, if it ranges from a negative number to a positive number, which means it contains 0, which means then this beta could be 0, which means there's no relationship between that particular independent variable that beta goes with and your y value or your dependent variable. So some common rules of thumb then, when you have non-significant independent variables, means that there has a relationship with the dependent variable, that is the non-significant independent variable. The independent variable should then be left in the model. So it's saying there's some type of relationship. It's not significant, but go ahead and leave it in. Sometimes this means it adds some value in predictability and reducing that overall error measure. Another thing you might consider doing is that if the model explains the dependent variable without the non-significant independent variable, then take it out and run the model again and see what your results are. The last sort of guide here on this slide is that what happens if b sub 0 is not statistically significant. That is, we don't know if it should be 0 or not. You should have a really good reason as to why you want to take that out. And what I mean by take out is leave it out of your model or your equation for predicting y. Another thing you want to look for when you're creating your models is something called multicollinearity. And that refers to the correlation among the independent variables in a multiple regression analysis. What that means is that if you have one x variable, is it correlated with another x variable? If it's highly correlated, meaning has an R value, probably 0.8, 0.9, or even 1, then that's said to have high correlation or multicollinearity exists. So when you have this, the problem is that you might conclude that a parameter associated with one of the multicollinear independent variables is not significant. That is, it's not significantly different from 0, when the independent variable actually has a strong relationship with that dependent variable. So that x, so we've got a couple of x's that are correlated. One of them may not appear to be strongly correlated with the dependent variable, and you would conclude wrong. You avoid this problem when there's little correlation among the independent variables. And I guess specifically, you can use the rule of thumb that if you have multicollinearity at a 0.7 or greater, then you probably need to exclude one of the variables. And that multicollinearity is expressed as a correlation coefficient. So the biggest problem with multicollinearity is that it increases the variance and the standard errors of the regression estimates. That is the betas for each of the x variables and the intercept, which means that predicting y is going to be less precise. So here we have the regression analysis for using those two variables, miles and gasoline consumption. That's out of your book. And we look at miles, the coefficient here, and we look at our p-value. So our p-value is a very, very small number. It's less than our alpha of 0.05. We would conclude that travel time is related to miles traveled. So we don't reject the null hypothesis. On the other hand, when we look at gasoline consumption and we see our beta 2 is a negative number here, we find that the p-value is 0.6588 if we round up to that last fourth precision point. So we don't reject that hypothesis. So we can see here that if we do a scatter chart of miles and gasoline consumed for the Butler Trucking Company, we can see that miles traveled and gasoline consumed are strongly related. And I'm going to stop right there, and when we come back to finish up this chapter, we will start with big data and regression. Multicollinearity continued.